Hello everyone. Um, so presentation about a paper we recently wrote, part of our team at YerevaNN, that works on radio signal propagation modeling, and it was part of a competition related to predicting indoor radio signal pathloss maps using few samples. So this is what the ground truths look like. These are maps. Each pixel has a color corresponding to a number. Each number here, the redder it is, the weaker the signal is at this particular point. This is the antenna, and you can imagine this is like a map of how strong a Wi-Fi signal is inside the room. And a lot of factors influence where the signal is strong or weak. Obviously, near an antenna, it will be strong, but the further you go from antenna, it's less and less obvious and less linearly predictable. You can see here patterns, for example, that run against the grain or against the line that comes directly from the antenna. These are due to effects called reflection, and I'll try to structure the talk in a way as to first introduce a bit how wave propagation works for radio signals, and also what we did to model them for the competition. Firstly, why do we care about this problem? And what is pathloss? Pathloss is a measure of signal strength that travels from transmitter to receiver. It's measured in decibels, so given some energy levels, linear energy levels, you can calculate the decibel decline in power using the logarithm of the linear power. Also, we are interested in this because the current state of the art for predicting the signal strength is ray tracing simulators. So the competition's goal is to model the simulator in a way, so to learn to predict the results the simulator would have given us without having to wait a long time for it to converge, and also without having to pay the expensive costs. The modern ray tracing simulators, commercial grade, they can cost up to $50,000 for a single station. Pathloss is also a fundamental property of signal propagation, and any advancement on this front will likely generalize to a lot of different tasks. Radio propagation is principles of radio propagation, and being able to model them correctly are very important for a lot of applications, like in military radars or things like driverless cars. For example, Waymo uses it as part of their sensor suite, and they can be crucial in situations where there is little visual content, like to orient yourself. And fast and accurate pathloss prediction can help us use it as a block inside an optimization loop. So if you can predict the pathloss at any point in a room accurately and quickly enough, you can use it as a component to optimize where do you place the antennas, how many do you need, and try to optimize for availability and bandwidth or signal coverage. So signal coverage would be can you place the antennas in such a way that the room has strong Wi-Fi signal at 90% locations, and also something like energy use. If you can put array of antennas that are weaker or cheaper and they still give you the same result, it will be economical. So how do you describe something like that to network, and what were our inputs? Our inputs were what are called reflectance and transmittance maps. Reflectance and transmittance are properties of radio waves. Reflectance is when a radio signal bounces off a wall. Every time it does that, it loses some energy, which can be measured with decibels, and the values written in these pixels represent the decibel loss in power if a radio signal were to bounce off a certain wall. And transmittance is when a signal passes through a wall. So you might have a Wi-Fi in another room and still get a signal, but it will be weaker due to factors, one of which is transmittance. We get two maps like this. We don't directly get where the walls are, so just implicitly through reflectance and transmittance maps. And they are same size as the ground truth, obviously. And this red star is the antenna location. We also get the frequency of the antenna and its precise x and y coordinates. Frequency is also important because it determines a lot of properties of the wave, like how quickly it will attenuate, how quickly it will get weaker, how likely it is to reflect off of a wall, or how likely it is to transmit. For example, high frequency waves are more likely to pass through a wall rather than reflect, and when passing they have high likelihood of scattering around and not passing a meaningful signal. So a lot of factors influence pathloss prediction. I wanted to talk a little bit about why this problem is not trivial to solve and why people spend so much money for ray tracers. So a lot of factors, each of them influences how the signal will spread, and they interact with each other non-linearly, making our lives harder. Reflecting off of walls, if a radio signal hits a wall at a certain angle, it will reflect off the wall at the exact same reflection angle. It can pass through walls. It can travel through air and lose signal strength. So there is what is called free space pathloss, and it describes how quickly the energy will lose strength, how quickly the signal will lose energy when just traveling through air. And other factors like diffraction and scattering. Diffraction is when a radio signal bends around the corners, and scattering is when it spreads around when it encounters rough surfaces. And high frequency signals are much more influenced by scattering, much more sensitive to scattering than low frequency signals. High frequency signals are like 5G, 6G antennas, and low frequency it would be like the radio. So low frequency signals are more robust, but they carry less information per unit of time. And there are constructive and destructive interferences. So if you have a lot of waves, you can imagine it like in a sea. If they sync up, their cycles sync up, they interfere constructively, and if not, they cancel each other out, leaving a weaker signal. So all of these are just part of the reasons it's hard to predict pathloss correctly. So what we did to model this is use a UNet architecture with a ResNet 34 backbone. We tried different backbones from 15 to 101, and this one was the sweet spot, probably due to data size, and we haven't seen any improvements going larger model sizes. We used asymmetric convolutions at the bottleneck to try to model long-term interactions. So by long-term interactions, I mean something like here you can see a reflection off of a wall. You can see this is a bit lighter. So in order for model to learn radio wave propagation, it has to understand that if there is a wall here and the incidence angle of the ray was alpha, this will reflect off of it at alpha angle, and here the signal will be better than it would have been had there not existed any reflections. So ASSP, we found, helped us in our Bayesian studies, and also visually it showed some improvements on this front. The training was done with just a simple regression loss, mean squared error on unsampled pixels. And what I mean by unsampled pixels is that for some of the pixels we have the values, correct values. You can imagine it as measurements that we do in the room. If you have an entire floor of a building and you have to predict the pathloss values at every location, you can do several measurements that will cover, let's say, 0.5% of the total area, and the goal is predicting the rest of the values. If you did measurements on all locations, you wouldn't need a model, but it would be too exhaustive and take a lot of time and a lot of measurements. And the goal of this competition was also to see how few samples are enough to predict the pathloss as accurately as possible at acceptable accuracy. Okay, so there were 25 different floor layouts, and these were the frequencies from 868 megahertz to 3.5 gigahertz signals, and for all of them we used the same architecture more or less, and used Adam optimizer and variable sparsity from 0 to 0.25% sparsity level. So we found out that training two different models for extremely sparse and relatively sparse scenarios gives us worse results than having one model trained on variable sparsity level. The other mode was 0.02% sparsity, so like 25% more sparse than this. Just a couple of pixels had ground truth values from which we had to predict the rest. And turns out training two models at 0.02% sparsity or 0.5% sparsity works worse than having one model with variable sparsity level determined at each sample. Okay, and the output was a single channel with decibel prediction of pathloss. Our model took 65 milliseconds to predict each map, including the pre-processing and reading the files and stuff like that. And our final result was 5.17 decibels, which isn't very accurate, but it's acceptable. Like, this is close enough that it could inform some decisions and be useful in optimization. I wanted to talk a bit more about free space pathloss. This part isn't like directly relevant to the methods in the paper, but it will be a bit educational and inform and explain why we used the features that we used. This is the formula for free space pathloss, where D is measured distance in meters, distance from antenna, and F is frequency in megahertz. And given this formula, you can calculate how many decibels of signal strength will be lost when traveling through air. This simple formula is used in a lot of applications. Like this is a lot of the state of the art before this competition, and a couple of others was using this and changing coefficients for 20. For urban settings, setting it higher, and any improvement on this is significantly helpful. Okay, I have little time, so I'll try to do this quicker. The features we used were the sparse measurement masks, so the same as the input transmittance and reflectance mask. Pixels that had ground truth values were set to their values and the rest were set to 0. We put log frequency and log distance from antenna as separate channels, and they are represented logarithmically due to their relationship in FSPL formula. We also added padding and cumulative transmittance loss, which is how much signal would have lost its strength traveling from antenna to a specific pixel just due to passing through the walls and incurring a transmittance loss. The augmentations were very standard and a bit limited because changing the values, like adding random noise, wouldn't be acceptable here because we would have distorted the physics. I won't have time to go over each of them, but I'll just concentrate on one of them, which is synthetic wall insertion. We saw that the network is sensitive to the density of walls in the room. So one thing we did is add extra walls and recalculate the signal strength according to these new added walls, which we pretended didn't have any reflectance values, so they wouldn't the signal wouldn't lose strength when reflecting off of them, but it would incur a transmittance loss. And also like things like flipping and rotating by 90 degrees, which our labels would have still been correct. Okay, a bit about strategic sampling. The idea was that because the nonlinear interactions are more pronounced and more dominant the further you go from antenna, our algorithm concentrated on the regions far from antenna, and also we wanted for them to be as spread out as possible. So the goal is sample the outer regions and also make sure that this point doesn't have a very close neighbor to it, like all of the other points. Okay, this is the algorithm, and it is O(n) square in terms of the number of points you want to sample. These were our results. This might be worth spending time on. So for very sparse scenario, the results are worse, like 35 to 45% worse than for even 0.5% scenario. And the final weighted average score we got was 5.17. You can see how few samples can help. This is like a matter of couple of pixels. So 0.02 is like 2 pixels in a typical room, 2-3 pixels, and this would be like 70 pixels. But the strategic sampling algorithm wasn't extremely useful. It was a slight help. Okay, the models are still very sensitive, and even though the pathloss values can be predicted reasonably accurately, we find that new floor layouts that are significantly different or have very different wall density will degrade prediction accuracy. This is probably due to limitations in dataset size, which was just a couple of thousand samples. And one interesting thing was that convolutional networks have really hard time learning reflection patterns. So transmittance, it would learn pretty quickly, and diffractions, we would notice convolutions could model reasonably well, but reflections, they struggled a lot. These are my co-authors. This was work done with guidance from Hrant Khachaturian and Theo Rabdis and Rafael Mukherjee and me work. So this is it on my part. Do I have time? I can revisit some.
Okay,
1 minute.
It's time for questions.
Let's start. Let's
Yeah.
stop here.
Thank you very much for the talk. I have the first question. I'm curious, is it possible to incorporate the knowledge about physical laws into the model? Not just give the data and ask the model to train on the data, but somehow incorporate the laws of physics into the model.
We tried to do that implicitly and with our input features. Like you can see, this is log distance and log frequency, and just from these two, the model should have been able to pick up free space path loss on its own. And we hoped that the model would do this, and I think it does that pretty quickly. The main thing that the model struggled to learn is just reflection patterns, long-term propagation. So it would learn to bounce the ray off of a wall, but it wouldn't like draw it continuously and lead to its conclusion. It's yeah, that was the main problem, I think, and also sensitivity to things like wall density.
Thank you. Do we have other questions?
Thank you for the talk. I have two questions. First off, I thought that you didn't take into account that the building has 3D structure, so you have only the projection, right? And the pixel intensity gives the measurement for that point, and it doesn't specify the height, right? And the second question is, why didn't you use transformers? It seems that they should take into account for the global correlations better, and is the data the limiting factor?
Yes, good questions. First one, why this is a 2D plane and not 3D? It's like the simulations were actually done, the simulations to generate the labels were actually 3D, but the data we were given was measured at 1.5 meters height. The transmitter was at 1.5 meters, and the measurements were done at that exact plane height. This just reduced the complexity, and you didn't need to take into account like occlusions due to objects that are not as high as a wall and non-line of sight, things like that. And it would be reasonably good estimate still. And regarding the transformer, before I joined the team, there was some work done with transformers, and they didn't work that well. But there were some papers, one paper that used transformer in a creative way and achieved good results, relatively good results. And I think the problem is that we just don't know yet how to leverage transformers correctly to model this. It's just you have to do some search in that space to figure that out. But I 100% think that as probably with all other problems, that transformer is the best architecture.
We have a time for the last question.
What? Just empirically, they beat every benchmark at everything and anything. And here the work that I'm referring to was part of this competition. And they didn't have fancy features, but the transformer was able to learn the reflection as far as I saw it on the few samples from the paper. I think if they had did a good grid search, tuned the hyperparameters, they would have won, and they didn't even have like fancy features to help them.
Okay, thank you.
You mentioned that RMSE was 5 decibels, around 5 decibels. So I wonder what is the production standard for this task. I recall 5 decibel is quite large number. It kind of doubles the energy. So what is
Yes.
acceptable threshold?
If you think in terms of linear energy, that is like very bad. It's like 10 to the power of 5 times error. But these signals aren't very strong that your devices register. They already have like path losses of around 50 decibels probably. So 5 decibel isn't very accurate, but it can inform you, give reasonable estimates to inform some decisions like where to place your antennas. And it's much better than using stuff like the statistical models that were prevalent before deep learning was applied. Like they would use formulas like this and have some extra coefficient and tweak this 20 a bit based on linear regression on some couple of measurements from a cityscape or a floor layout, and use this as approximation.
Okay, thank you once again for the talk.